Hi everyone, so this is a video where I want to make some correction to the previous video on my derivation of the equation for pressure. So yes, I'm sorry I made some mistakes, and the mistakes is a bit subtle that I only realized that after I posted the video. So this is the part where I want to correct. So the error is a bit subtle, so let me show you. Okay, let me just write this really clearly that this is incorrect. And let me show you what would be correct. Okay, so in step 6, what we did last time was we want to generalize it to 3D velocity. Okay, so okay, so we know we previously from step 5 we end up with this equation, pressure P equals to mn Vx square over volume. So with this form, what we did last time is we want to generalize it to cover for a range of speed. We have high speed, we have low speed, we have moderate speed. So previously we assumed that they are the same, but now we want to do something to take away this assumption that they are all the same. So we replace this Vx square with the average of Vx square. So the correct thing that I should write is it should be mn Vx square average. Now it might seem like the same for you, but it's actually different. What you see here on the left, Vx square average, is different from what you see on the right. Vx square bracket, then after that average. What's so different about it is for the steps on the left, okay, if I write it like this, what will happen is, okay, what will happen is you can think of it as you take Vx, average it, and you square. Okay, so this is the average is your step 1. Okay, let's use another color. The average is your step 1, the square is your step 2. But that is not what we are doing. What we are doing is actually we square it first. That's our first step. We square it first, then only we find our average. That's a bit different because why is it different is if you draw a graph, okay, so let's say this is the velocity, ms -1, then this is the number of particles having that particular velocity. So you use something called the Maxwell-Boltzmann distribution, our syllabus. But essentially what I'm trying to say is you will see that the number of particles that are having positive velocity should be equal to the number of particles having negative velocity. So what I mean is the number of particles at this region, this is called high speed region, for negative direction and positive direction should be the same number. So if you take an average, right, this part and this part, eventually they will cancel out. Okay, the same thing for the middle part. Let's say for this area here, moderate speed, the number of particles having moderate speed in the negative direction will be equals to the number of particles having moderate speed but in the positive direction. So what essentially, when you do an average, these two parts will cancel each other out as well. Actually, what I'm trying to say is the whole area here for negative velocity will be cancelled out by the whole area here, which is having positive velocity. For every high-speed particles moving to the left, you will find another high-speed particle moving to the right, because we say equal number of particles moving to the left, equal numbers of particles moving to the right. So for every low-speed particle you see going to the left, you will see another low-speed particle going to the right. So actually, if you average them, left and right cancel each other out, so you end up with 0 average velocity. So to get around this 0 average velocity, which is meaningless, you don't want 0 as your answer, what you do is you square first. So when you square the value, we know all these things here are negative velocity. But once you square it, then you become positive velocity square. Okay, whereas this side, if it's positive right now, if you square it, it will still be positive. So now, if everything is positive, there's no negative and positive to cancel each other out. Okay, everything is positive, so when you do a sum and then you get an average of things, you won't get a 0 as your answer because there's no cancelling out. Everything is positive, so you eventually find an average, but this average is an average of velocity in the x direction square. Okay, velocity in the x direction square, that value you find the average. Okay, so that's why the first step should be square and the next step should be average. If your first step is average, like in this case, the incorrect case, if your first step is average, your answer will be 0. Then 0 square will be 0. So they are a little bit different in terms of the writing, but they make a lot of difference. So be really careful when you are writing. Okay, so that's my mistake. I really apologize for it. So let's continue. What are we going to do now here is we want to change the velocity in the x direction. We want to generalize it into the actual velocity that we have. Of course, we will still use the average approach, just that we want to change it from x component to be a combination of x, y, and z, the generalized velocity. Okay, so what should we do here is we will need to see how can we relate this term over here, this vx square average, how do you relate it to v square average? So to do that, we will need to know that v square average v equals to vx square average plus vy square average plus vz square average. So notice things is a bit different from last time. Last time I used to have a square root over here, but if you see here, if I put a square root for now, what will happen is if I square it, it will be average square. So v average is equal to 0 already. If v average square, then it will continue to become 0. So that's the flaw of what am I doing just now. I'm not supposed to do it in v average, because v average should definitely get 0 because the left and the right cancel, the up and the down cancel, the front and the back cancel. So that's not what should we do. We should do it in square form. So this is what should we do. We don't do the square root here. So just now as we see, we want to transform this vx square average into v square average. So let's change all the vy and vz to be in vx. As what we said in the previous video, no matter which wall you pick this wall, you pick this top bottom wall, you pick this front back wall, you will still get the same equation, and there's no bias in which direction should move faster, which direction should move slower. There's no such bias. That means by vx square average should be equals to vy square average should be equals to vz square average. So in that case, we replace everything with vx square average. Okay, so these three things are the same, so I can put them together to form 3 vx square average, and this will be equals to v square average. And now, since I'm going to replace this vx square average here, what should I do is I should put that to the left hand side, then the rest to the right hand side. Okay, so that's what we have done. So now let's transform this thing here. We put this thing to replace this vx square average. Okay. So P previously was mn Vx squared average over V. So what we do now is we change it to mn 1/3 of V squared average divided by the volume of the gas container. So now if we rearrange it a bit, it will be 1/3 of mn V squared average divided by V. So that is the formula that I'm actually trying to reach for. If you notice, the difference is this one is V. The previous incorrect one is we average only we square. Now it's square only we average. So there's a little bit difference here, even though it's subtle, but it's still important that we able to differentiate it. This is wrong. This will end up with 0. This is correct because you square to make the negative velocity become positive first. Only you find the average. Okay, so there's another thing that we know is if we are doing average in mathematics, average or mean, we represent it with this symbol, which is this kind of bracket here. So if you are finding the mean of x, then it will be something like this. So for this case, we can change the way we express this symbol. So this symbol will be 1/3 mn. So we're finding the average of V squared over V, the volume of a gas container. So this is actually the formula that I'm trying to go for, and this is the formula that is being introduced in your syllabus. Okay, so one interesting fact that we should know about is this mean of V squared here is actually the square root of the average of V squared, right? So we can relate it to something called root mean square. So let me write in green color. So root mean square, it's a very useful technique in finding average for something which average out to 0. So root means by square root. So square root of the mean of the squared value. Okay, you square root the mean of the square value. So what you do is V root mean square is actually equals to you square something and you find an average of that square. So then after that you square root it. So we also call this as VRMS. Okay, root mean square speed. So if we match it to the situation we have here, our equation here we have 1/3 mn V square mean divided by V. So this is also equivalent to VRMS square actually. So you can also replace this to be VRMS square. So let me bring this up here. So this P here will also be equals to 1/3 mn VRMS square divided by V. Okay, how do we build this VRMS square equals to mean of V square? We build this using this idea here. Okay, it's the square root of the mean, this bracket here, of the mean of the squared value. In this case, we are finding root mean square speed. So the square value of speed, you take a mean of it and you square root it. So this is exactly the representation. So if you want to be really specific, then you can see that VRMS square just equals to this mean of V square. That's why we can replace this V square mean with VRMS square. So that's the idea behind this thing. So that's all the correction that I want to do. I'm really sorry about it. But yeah, here's a correction for this average thing. Okay, thank you very much.